of the gas laws, we're going to look at Boyle's law. And in the gas laws, we're looking at the relationships between pressure, volume, and temperature. And we start by looking at the relationships between two of those variables at a time. So what is going to be kept constant as we look at Boyle's law? And looking at the table, the number of moles is being kept constant and the temperature is being kept constant. So in our lab, we're going to investigate the relationship between volume and pressure, and providing the temperature remains a constant, as well as N, the number of moles. So we're going to use some equipment, and this one here is involving a pressure gauge and a syringe. So pause and predict, write down what you think will happen as you push the plunger of the syringe inwards. And once you've done that, here we go and look at the equipment. You're going to wear goggles, a lab coat, and care with higher pressures in the syringe. So you're going to separate the syringe from the pressure gauge tubing, and the plunger is out. So you've got air at atmospheric pressure in the syringe and air at atmospheric pressure in the tubing going up to the pressure gauge. And you're going to collect data, and this will be your data table. You're only going to fill out the pressure and volume columns and leave the fourth column empty for later use. So our first trial is once you've reconnected the syringe to the pressure gauge at atmospheric pressure and record the results as accurately as you can in your data table. So this is trial number 1. Then we're going to look at a number of other trials. So pause to make sure you've got both readings correct before going on to the next trial. So for trials 2 to 7, if you were doing the experiment, keep the difference in volume to less than 10 mils as you push it in each time, and record both pressure and volume. And if you were doing this experiment, note any qualitative data. So this is trial number 3. Pause to get the data. Trial number 4. Trial number 5. Trial number 6. Make sure you pause so you can write it down as well. And trial number 7. So now you have completed the table, and the first thing we're going to say is we're going to multiply pressure and volume, which is exactly what Robert Boyle did. And so look at that fourth column, P times V, and what can you say about the numbers you obtain in that fourth column, and what does that then actually mean? So pause to complete that activity. We're going on to draw a graph. So start just looking at your data table and predict what your graph would look like. Straight line, curve. Will it go through the origin? And work through that before you start plotting your numbers. And if by some chance you're at home and haven't got graph paper, if you've got lined paper, turn it into squares. So a little bit of measurement and accurate drawing. Otherwise your graph will not be as helpful as it can be. So you're going to get a graph, a curve or a line. You'll see what you're going to get, and it doesn't go through the origin. If we want a line to go through the origin, we virtually need a line that is perpendicular to that one. So here we have a downhill slope with a negative slope, negative gradient, and we need a reciprocal of that slope to get a perpendicular line. So what you're going to do, really add to your table, add a fifth column to it, and you're going to put in the value of 1 over V. So this is what you are doing as you are analysing your results. So what we're discovering is there isn't a direct relationship, but we actually have an inverse relationship. So if you plot pressure against 1 over V, but you have to plot the decimal value, not for the fraction. And so another question that we've got here, what happens if you reduce the pressure? So separate the syringe from the pressure gauge, push in the plunger, and then reattach them as shown in the diagram. And you're reducing the pressure by pulling the plunger out. So what's going to happen to the readings? And pause to think about that one. So Boyle's law in words, the pressure of a fixed mass of gas is inversely proportional to the volume, provided the temperature remains constant. And we can look at that mathematically with symbols. P squiggle, P is proportional to 1 over V, proportional to the inverse of the volume. And in order to remove the proportionality sign and get an equal, we're going to put in a constant. So P equals constant over V, and K is the constant slope of the graph. So for the first trial, P1 equals K over V1, which we can write as P1 V1 equals K. For the second trial, P2 equals K over V2, P2 V2 equals K. And so I can put, because they both equal K, I can put P1 V1 equal to P2 V2, and that is Boyle's law. So if we know 3 of the items, P1, V1, P2, we can calculate V2. And that's how it becomes useful. And so here is a calculation. So calculating how the volume of a balloon will change at a different pressure. So we've got a party balloon here, a fairly nicely shaped one here, with a volume of 45.5 litres at sea level, 1 atmosphere pressure. And what will its volume be at an altitude of 5,000 metres? The height isn't going to be in the calculation, but the pressure is less with increase in altitude, and here it's 0.54 atmospheres. We have to assume the temperature doesn't change. In reality, it does get colder as you head upwards, so it'd have to be inside an insulated container, and assume that the amount of gas does not change. And so if you use this method every time, you shouldn't get your calculations wrong. Define the variables every time with their units, and also state in terms of letters what the rule is, so you substitute them correctly. So you've got V1, P1 and P2. It's your V2, which is question mark litres. Plug that into the Boyle's law and solve for V2, and you get 84.3 litres. Now consider, does that seem reasonable for that balloon? We'll assume it doesn't burst. So think about that. And then a little bit about Robert Boyle himself. And you can pause to look at some of the things that he did, certainly not his entire life here, and look at the period within which he lived. Did some interesting things with other scientists and following what they had done, and devising methods to measure pressure. And we look at this one where he produced a water barometer. Often barometers in the early days were sealed tubes of mercury, where the sealed was at the top and the mercury tube was opened under a reservoir of mercury. And if the tube was long enough, the level of mercury would drop because the air pressure could only sustain about 76 centimeters worth of height of mercury. Water is over 13 and a half times less dense, so the column of water is over 13 times taller, and that's what he did, attached this equipment to the outside of a building to measure atmospheric pressure. Do not do this at home, please. Another application that we use in everyday life, inhaling and exhaling with the volume of the lung. So the muscle just at the top of your abdomen underneath the lungs, the muscle contracts and moves the thoracic cavity, the lung cavity, downwards, increasing the volume. So there's lower pressure in the lungs. Air pressure at the atmospheric pressure is now greater, and so travels into the lungs. When you exhale, the diaphragm relaxes, moves back upwards, the lungs contract, there's a decrease in volume, so the pressure inside the lungs increases. It's greater than the air pressure outside, so air is now exhaled. So some useful items, and you'll probably think of quite a few more. And we've also got studies of Charles' law, Gay-Lussac's pressure law, and the ideal gas law for you to look at as well. Thank you for listening.